Okay, this is lecture number 18 of the course AU 203 Statistics and Quality Control. So far we have talked about discrete probability distributions like binomial distribution, Poisson distribution, and a generic case we have seen for a discrete distribution. Now we are going into the concept of continuous probability distribution, and in this lecture we will go into this first start with the continuous random variable and discrete random variable, and then the concept of continuous probability distribution, and then we will go into the probability density function we call it, which is exactly the same thing as probability mass function for a discrete random variable. Its counterpart is probability density function if your random variable is a continuous random variable. And then we will look into the expressions for calculating the mean and variance of continuous random variable. And in the end, we will start in a very important continuous probability distribution, that is normal distribution, but we just would look into the concept part, and in the next lecture we will go into detail about the normal distribution. Okay, so let's say you have a continuous random variable which can take infinite number of possible values and within the given interval. So the continuous random variable is can take any value in the given interval. For example, we have a number line which is representing numbers from 0 to 468. So there is an interval between x1 and x2. It could be between 2 and 6, or between 4 and 6, or between 4 and 10. It could be any interval. And what we observe here is this in this interval, the values of a random variable is a continuous. It can take value 2, it can take value 2.1, it can take value 2.5, it can 2.7, it can take value 3.719, it can take any value in the given interval. So once we say any number can come in, so any number in this definite interval from x1 to x2 can come in. So it could be any random variable. Okay, so let's say if your range of your random variable extend over an interval, either it is a finite or infinite, and we can represent it on a real number line, then that random variable would be called as continuous random variable. And we have seen that the formal definition of a random variable is you take some values from a sample space and you have certain function which transform that values from sample space into a number line, and if it is discrete values, then it would be called as discrete random variable. And if it is a continuous random variable, then it would be if it is a random variable is continuous, it is it could be any value in that given interval. There are several examples. Let's say, for example, if I am interested in knowing the height of the student in a class, so some or weight of the student in a class, so some would be very tall and some would be short. So if I measure the height of each student in a class of 50 students, let's say, then the numbers comes would be different centimeters, or if it is in pounds, or if it is in kilograms, I could get different weight. So each any number, if I pick it from any student I pick from the class, it's if I record its height or weight, I could get any value which can be represented on a number line, and it could be a value in decimals, or it could be a value, integer value, it could be a negative value, it could be any number. Okay, let's say, for example, if I'm interested in knowing the time that is actually used in performing a certain task. So the time can be measured, let's say, in minutes or hours or days or whatever, in seconds. So I could take any number can come in. So that would be considered as a continuous random variable. Let's say a bag of sugar that has to be packed by a machine, and let's say it's a 5 kilogram bag. So not all the bags would be exactly 5.00 kilogram. Some would be 4.95 kilogram, some would be 5.05 kilogram, something like that. Any number can come in this interval. Let's say if I'm interested in knowing the life of the light bulb, let's say 100-watt bulb. So some bulb lasts for 2000 hours, some for 3000 hours, for 350 hours. So it could be 3.5 hours, it could be 0.75 hours as well, or it could be 0.001 hour. Just in the beginning it starts failed. So the lifetime would be distributed randomly, and the value you get for that random variable, if it can be represented on a continuous number, real number line, then it would be called as continuous random variable. Okay, so discrete random variable would be something always countable and finite, whereas continuous random variable would be actually you are counting as well as you are measuring, and you are getting number which could be finite number or which could be infinite values in a given interval. So this is the feature of continuous random variable. Okay, we will look into more detail about, let's say we have uh, probability distribution of a random variable. So as we know, random variable can take any value. Let's say what is the probability distribution of a continuous random variable. So as we know, there are so many physical systems where we are dealing with variables which are continuous variables. For example, let's say there is a beam, and we are interested in knowing the loading per unit, how much is the force which is acting on the beam per unit length of the beam. So for example, once x is close to 0, the loading is 0. As x increases, the loading is increasing, and so this variable x here would be called as a continuous variable, because at any point x along this its corresponding probability can be represented by some mathematical function, and that mathematical function we call it a probability density function. So here, for example, in this particular case, as you are going away from the x-axis is increasing, the amount of loading is increasing. So higher values, the corresponding probability that you will find the loading for a particular random variable, it is increasing as x is increasing. Okay, so let's say we have this graph which is actually showing the wave height that has been determined experimentally. For example, some waves, for example, this one is 1 meter height, this is the probability, and 2 meter height is this probability, 3 meter height is this, or it could be even 2.5 meter has this corresponding probability, and so 5 meter height is more probable. Over 18% is the probability of getting a height 5 meter. So here this height of a wave would be considered as a continuous random variable, because it can take any value from 0 to 12 or 15 or up to 20 it can go, but there is a very small probability of getting a wave of height 11 meter or 12 meter or nearly 0. So it is quite safe to build something where your height should be, your ground level should be higher than 12 meters, so that the maximum wave that could hit would be which is very less probable, but it go up to 12-meter height. So this graph is actually representing the probability density of that random variable, continuous random variable, which is the height of the wave, and the mathematical function which is representing this probability of that random variable would be called as probability density function. Okay, so for a continuous random variable, a probability density function is just like the same as the definition validity for a probability mass function. If your random variable is discrete, you have certain criteria that its probability must be positive or greater than 0 and less than 1, and the sum of the probabilities must go to 1. So exactly the same conditions lies with if your random variable is a continuous random variable. Let's say capital X is a continuous random variable, and it can take different values, and these values are represented with small x, and the second condition is the sum of the probability. So sum of the probability means whatever the probability density function is, if you integrate it over all values of x, that is from minus infinity to plus infinity, your sum would come out to be 1. So just replacing sum with a sigma notation with an integral which is representing continuous random variable. So once it is continuous, so we represent it by area under the curve, and for a valid probability density function, if your x is a continuous random variable, then your area of the integral must come out to be 1. And obviously the area under the curve between the two intervals, let's say x can take value from a to b, then the probability between a to b would be the area under the curve from this limit a to b. So it is quite easy. If you know the probability density function, you can easily calculate by just summing up in that interval. You will be able to calculate the corresponding probability in that interval. Okay, let's say we can represent it. Let's say f of x is some function, and from minus infinity to plus infinity, its area under the curve is unity, and its probability would be obviously this shaded area would be smaller than 1, because the whole area under the curve is 1. So in that interval it would be representing some number less than 1, which would be representing the corresponding probability in that interval. Okay, here x can take any value, and the corresponding probability can be easily worked out by calculating the area under the curve if you represent the distribution by a mathematical function. Okay, let's say the histogram is actually just like you always see that in discrete random variable, the distribution is represented by a histogram. So correspondingly, if you make the width of the histogram much smaller, then what we can do is these discrete formation can come into a continuous formation, and so the area under the curve would be representing the probability in a given interval, and if it is from the minus infinity to plus infinity, then the whole area must be equal to 1 in order to be a valid PDF. So let's say, for example, if you have a question like this, and your random variable can take any value in the interval from a to b. So if I am interested in calculating the values which is equal to a and greater than a, as well as equal to b and less than b. So is it the same to write like this? So instead of calculating up equal to a or greater than a and less than b, the area under the curve remains the same. So obviously, since the area under the curve remains the same, then the two probabilities would be same, because it doesn't have any corresponding probability when x equal to a. So the probability always lies in an interval from a to b. So either way you can write. And from this particular fact, we can learn that for a continuous probability density function, the probability value at a particular value always come out to be 0, whether it is the point A or whether it is the point B, where the value of x is A or whether the value of x is B or any other value, because at that particular point there is no area associated. So area under the curve is 0. That's why the corresponding probability is 0. So in continuous probability distribution, the probability always is between certain interval, and the area under the curve of that interval represents the probability. So there is no point in representing the probability at a particular value. You always need to denote probability in the interval from x1 to x2 or a to b, any interval. Okay, so this fact we have learned. So the probability for a continuous random variable is exactly equal to a number would be 0, because the area under the curve is 0. Let's say if x is a continuous random variable, we can say there is no point whether it is greater than equal to or less than and equal to, or greater than a and less. So all this one and all three are actually the identical statements. Okay, now let's see the problem, how we can look at the problem. Let's say suppose x is a random variable representing the mass in kilogram of a substance produced every minute of an industrial process. So let's say and whose probability density function is this. So f of x represents the probability to calculate the probability. For example, if x lies equal to greater than 0, or if it is equal to 0, then f of x comes out to be 0, or if x comes out to be 6, then it's also 0. But if it is anything greater than 0 and less than 6, the corresponding probability can be worked out from this expression. So the point is, find the probability that the mass is more than 5 kilogram. So your random variable can take any value. This mass of a substance in kilograms per minute of an industrial process can take any number. So we have to calculate the probability when the mass is more than greater than 5 kilogram. So let's say this function, if you draw that function, because is a parabolic function, you can draw it. When x is 0, you are here. When x is 6, you are here. And when x is 3, you have a maxima here. So you have this sort of curve, and your valid range always lies between 0 and 6. Anything less than 0 has no meaning, anything greater than 6 has no meaning. So what we need is to calculate the probability when x is greater than 5. So 5 to 6, we have to integrate this in order to get the corresponding probability. So when the probability, your random variable, is greater than 5, it means you need to integrate from 5 to infinity. And here infinity means 6 here, because your maximum value is 6 here. So you go from 5 to 6 and you integrate that expression and put the limit 5 to 6. You got this area under the curve that would be representing the probability for a random variable would be your mass in kilograms would be more than 5 kilograms. So you just integrate this expression and you got the probability, and probability comes out to be 7.4%. Let's say what would be the probability? The mass would be greater than 2 and less than 4. So you need to integrate this expression from the limits 2 to 4 to get the corresponding probability. So this is how you can easily calculate the probability, and if you integrate the whole thing, if it is a valid PDF, then if you integrate from 0 to 6, then your area must comes out to be unity, because otherwise it won't be a valid probability density function. Okay, another problem, let's say you have x is a random variable where the probability density function can take values in this function, and x can take any value between 2 and 4. So what is the value of c that makes this a legitimate probability distribution? So we already know that for a legitimate probability distribution, whatever the value of x is, if it's f of x must be a positive number, and area under the curve from the limits minus infinity to plus infinity comes out to be 1. So we just need to integrate this expression, because our limits are from 2 to 4 and c x to the power cube, and this area under the curve must be equal to unity for a legitimate PDF. Then only unknown in this equation would be c, and we can easily calculate the value of c. So c comes out to be 1 upon 60. So if your function is 1 upon 60 times x cube, then in this limit it would be a valid probability density function. Let's say another problem where you have, let's say at this the same problem 1 upon 60 x cube. I just have substituted the value of c, and I'm interested in calculating the probability when x is greater than 3. So what I need to do is greater than 3 means integrating it from 3 to infinity, and here infinity is 4. So because the maximum value comes out to be for that function is 4, because otherwise if it is 0 or negative, then this would not be a valid PDF. So integrate from 3 to 4, you will be able to get the probability, and for probability x greater than 3 comes out to be 72.9% in that case. Okay, the next question is, what is the median of this distribution? So let's say we assume that small m is a letter to represent the median of the distribution. So I don't know where the curve, how the curve is, as I know that it is a cubical curve, and if I am moving from 2 to some value m where the area under the curve is half. Half is because I am in the middle of the region. So because median is the middle value of the distribution. So the middle value means the area under the curve comes out to be half. So I just integrate this expression, and I end up with the value of m comes out to be 3.415. So that would be the median of that distribution. Okay, the next question is, what is the cumulative distribution function? So as we already know, the definition for cumulative function is represented always with a capital letter, and which would be the probability when your random variable is less than and equal to x, and x is that threshold value. So if you recall back the cost of the books for different books, we had that idea for cumulative frequency distribution. So whether your cost of the book would be less than $20 or less than $30, and $20-$30 would be your threshold values. And so this random variable can take any number, and this mathematical function which actually takes care of this probability for any random variable which is less than equal to x would be representing the cumulative distribution. So here I can easily calculate that, because I need to go from minus infinity to some value of threshold value x, and if I integrate that probability density function, then I will be able to get the cumulative distribution function. As I know that the cumulative distribution function is in terms of x, so that's why I have not written f of x. I have written a dummy variable tau. So whatever the function is, you just substitute here and you integrate that function, and once you put the limits, because in your limit x is present, so once you substitute the limit, your final answer would be in terms of x. So that is the way by which we usually write in continuous distributions, because the reason for writing this dummy variable tau, or any variable, you can put t or y, you can put any variable, because whatever the function is, if you integrate that function and if you substitute the limit, and the value of x is present in the limit, so then this result would be in terms of f of x, capital F of x, which would be some function of small x. Let's say, for example, for this particular case, if you have to calculate the cumulative distribution function, so I integrated from the lowest value 2 to some value of x. So, and x can take value from 2 to 4, as I know, then this function would be representing its cumulative. So what you learned here is, once I need to calculate the value x is less than equal to 2.7, then I just need to substitute x equal to 2.7, and then I will be able to calculate the probability for x is less than 2.7, or from this cumulative distribution function when f is comes out to be 2.7. Okay, so this is how you can calculate the cumulative distribution function. Okay, then the questions of calculating the mean and variance. So the definition for mean is exactly the same, whether what it is in the discrete distribution, the same is in the, so expected value is just taking the sum of x and corresponding probability. So we used to represent p of x by the corresponding probability, and here this mathematical function with representing with the small letter f of x is representing the probability density function PDF, and if you multiply by the corresponding value and take the sum in that interval, you will be able to calculate the mean value of the random variable, where x here is a random variable which is a continuous random variable. And the variance can be easily worked out exactly in the same manner when your random variable is having a difference with the mean, and take the square and calculate the expected value. And obviously there is an alternative definition, you know that. For this variance, which is the square of the standard deviation, if you integrate instead of x, x minus mu whole square, if multiplied by that function and integrated over that, you will be able to calculate the variance. So if you know the f of x, you can easily calculate the mean as well as the variance of that distribution, continuous distribution. So here, for example, this can be written in this alternative form. So first you take the expected value of x square, which would be x square times that function, and integrated it and subtract it with by expected value and take its whole square, and expected value is the mean. So this is how, this is alternative way of calculating the variance of a continuous random variable. Okay, let's say you have a continuous random variable with the same function 1 up cx cube, or the value of c is 1 by 60 here for a legitimate PDF. So let's say if I have to calculate the mean value, so mean value is nothing, just multiplying the value with its corresponding function and integrate between the limits. So limits are 2 to 4 and x is the value and its corresponding probability is 1 upon 60 x cube. So you just multiply it together, so it would be x4 upon 60, and if you integrate that, you will be able to calculate the mean value. So mean value comes out to be 3.3 in that case. And obviously the variance you can work out by integrating it x square times the function and subtracting it with the mean. Mean is already 248 by 75 and take the whole square. So if you integrate this expression and simplify, you will get the probability, you will get the variance which is 0.266. So average is 3.33 and the variance is 0.266. And if you have to calculate the standard deviation, take the square root of 0.266, you will be able to calculate the standard deviation of that continuous random variable. Okay, now we got this general concept of continuous probability distribution. So here, let's say we have a college where we have 3,264 female students, and what we are recording is, we're recording the average height of these students, which comes out to be 64.9 inches and standard deviation is 2.4 inches. So it means height in 56 to 57 inches, out of 3264, 3 people would have this height, and between 57 to 58, 6 female students would be having this height, and 58 to 59, 26 females would be having this height. And as you know, if you just calculate the probability, 3 divided by 3264, you got this number, or 6 divided by 3264, you got this number. So this is something called a relative frequency, and you're actually the sum always comes out to be 1. So 1 over 3264 is that small number. So now we have to look what type of distribution it is, because height here is a continuous random variable which can take any number in the given interval. So if you draw its histogram, and you can see in that 60 to 61 and 61 to 62 and 62 to 63, so the numbers, the relative frequency is plotted, and you can see this the maximum value comes out in the order of 0.17 something. So 0.17 something is the maximum value, and here the mean value is 64.9 inches and standard deviation is 2.4 inches. If your total number of observation in this is, and we can use the Minitab to draw such graphs. So this is showing the height of those 3264 female students, and we can see this is a smaller height, lesser height, and this is an average height in inches, 64 inches. As you know, there are 12 inches in 1 feet. So if it is 60 inch, it means 5 feet. So obviously it is higher than 5 feet 3 inches, 5 feet 6 inches. So average height is 5 feet 5 inches something. the average height, and there is some female student is having a higher height. So you once you just have those midpoints and you just make this width of this bar frequency bars, if it's smaller and it's smaller, so you will be able to get a continuous curve. So this is a typical normal distribution of the height. Some would be having a small height, some average is having a this height, and taller would be small in proportion. Shorter and taller are small in proportion, so that is represented by this tail on the left tail, on the right tail, and the middle is representing the central tendency of the data. So this is a typical distribution of this continuous random variable of height, and typically it is a normal shape of the distribution. So the shape of the distribution is important here. Okay, from let's say 17.13% students have a height in the range of 64 to 65 inches. So 64 to 65 inches, 17% of the female students would be having, and most of the female students would be having this height. So area under the curve always comes out to be unity. That's why the sum is unity, and for every random variable it's corresponding the mathematical function which represent that distribution. If you calculate that function, it would give you its corresponding probability. And if you plot for all these possible values in a given interval, we will get this probability distribution curve. Okay. So this particular distribution curve have for example, if I have to ask how 68 inches or greater than 68 inches, so this would be the area under the curve, and which represents only 9.824% is the probability that if you pick any female students out of that population, and you are going to get height greater than 68 inches. So this is a typical well-shaped curve, and we call that curve to be a normal distribution curve. This curve has particular characteristics. For example, here random variable is continuous, and the height is distributed symmetrically. So if you make it a mean value, so the whole area is divided into two halves. So if the whole area is 1, then less than 64.9 would be the area 0.5, and greater than 64.9 would be area 0.5, and then 0.5 and 0.5 would make this area under the curve equal to 1. And we see that the range of the values for this random variable can lie from -infinity to +infinity, because it can take infinite number of values. But obviously for smaller values you have very less probability, and even for higher values you have very less probability. But the central tendency of the data lies with the mean value of that distribution, which is actually in the middle of this distribution. If you see that from this particular example, the mean height of the female students comes out to be 64.9 inches, and the standard deviation comes out to be 2.4 inches, and this shaded area represent the height of the percentage of the females or the probability of finding a female. 9.84% is the probability that that their height is greater than 68 inches. Or if I have to calculate the probability less than 68 inches, would be 1 minus 0.09824. So represent that area. I can easily calculate the whole area is 1 and this area is 9%. So 100 minus 9.824% would be this whole area. So the probability of getting any female having height less than 68 would be, once I know greater than 68, 1 minus less than 68, I can easily calculate. So this is where I stop today's lecture.